Right, so welcome back, everybody. So the last talk of the morning session is by Meisam Razaviyayn from USA. Take it away.
Well, thank you very much, Kostas. It's a pleasure to be here. So today I'm going to talk about solving certain classes of non-convex minimax optimization problem. This is a joint work based on my works with many colleagues, but the parts that I'll focus on mostly is a joint work with my student Babak, Andrew, and Dimitri was in the job market this year. So we have heard many interesting talks about min-max optimization problem. This talk is also about min-max optimization problem. I'm going to make some assumptions throughout the talk. Basically, I'm going to assume that you have a min-max problem, that your constraint sets are closed and convex. These are going to be assumed throughout the talk. I'm going to assume that your function is smooth, L smooth, Lipschitz continuous gradient. It could be possibly non-convex. Basically, our focus is non-convex, although some of the results that I'll talk about, they are generalized, and we have generalized it to stochastic settings and some non-smooth settings that they proximal friendly. There you can easily extend the results. And what I'm going to do is I'm going to start with some motivation very quickly, because we have heard a lot, and some applications. The application will help us to also talk about and motivate what do I need from an algorithm, and talk about some solvable cases. And by solvable, I put it always in quotation marks because I'm going to talk about what do I mean by solvable. And essentially, what we are going to see is that this problem and the notion of solvability that we'll talk about is solvable. And there we talk about some algorithms and convergence rates. When, for example, your f, objective function, is concave or strongly concave in alpha, it could be non-convex in theta. You see that it is solvable when there is a small coupling between the two variables, meaning that the Hessian of f, when you take the first derivative with respect to theta, second derivative with respect to alpha, this coupling is small. And also the third case, when the radius of the set A is small, see that these are the cases that we can develop some efficient algorithms for solving. And please, throughout the talk, stop me and ask questions if you have any questions. So let me quickly give you a simple motivating example. Motivation for us in this talk is, one motivation is designing robust systems. You know that when we want to design a system, for example, minimize the cost, minimizing the energy cost, something else, error in your, for example, classifier, you typically minimize your objective with respect to some nominal value of parameters, let's say alpha naught. But when you want to have a robust design, you may allow some perturbations of alpha, and you minimize for the worst case. And that leads to a min-max optimization. This appears in many different domains, ranging from, for example, robust design of beamforming design and wireless communications to adversarial defense against adversarial attacks, that we have seen a lot of examples of it during this workshop. It appears in other applications, such as GANs, training fair machine learning models, distribution, robust learning, all of it that other speakers talked about, so I'm going to skip. So you have seen slides like this a lot. We have seen it a lot during the past talks as well. So our non-convex min-max problem is challenging to solve. And to understand it, I'm going to compare and contrast it, put it side by regular minimization. So, for example, I want to train a regular network. I want to train a robust that basically in the left-hand side problem, left-hand side of the problem, you want to find the best parameter W, so that given your input data X, you have the minimum training loss. And this L is, you can think of it as an ERM loss summation of all losses. The right-hand side is, you consider for worst case perturbation. at delta. That is basically you'd solve a min-max problem. And so we saw some hardness results this morning. Manolis had a very nice talk about like hardness result. But I'm going to talk about basically in practice. Are the problems that we see in practice, are they really hard? Or like the difficult case doesn't appear in practice. So when you have a regular minimization and you give it to a practitioner, they typically, for example, we can run gradient descent. It has some nice properties. The nice properties are that the objective function improves over iterates, meaning that if you start running the algorithm and you stop it after 1 hour, you most always we know that we are at a better point. For example, now you run projected gradient descent or gradient descent. The algorithm is dimension independent, converge iteration complexity, meaning that we can run gradient descent on huge scale when the number of parameters are large and still have expect fast convergence. It is very well studied. We know the iteration complexity upper and lower bounds. But on the right-hand side, one of the popular approaches that's used a lot in practice is gradient descent ascent, for example, that today we have seen also a lot of examples of it. But is this algorithm convergent? I know that we have seen examples such as x times y, like w times delta example, that this diverges. You have limit circles. But I'm applying this gradient descent ascent algorithm to training a robust network, okay? And also a regular training. And basically what we did here is a simple small neural network with on MNIST data. We compared the regular minimization with the min-max formulation, this type of minimization. We ran 10 epochs for different step sizes. We randomly choose a step size within a range that we knew that like there are almost convergent results. And you can see that most of the times, so the x-axis here is the accuracy that you get. And this is the histogram out of like 50 runs that we had. And we chose different step sizes for each run. Okay. And you see that for regular minimization, most of the times you get the accuracy which is close to 100%. Okay, but you have also failures. But when you do this formulation or you follow this dynamics, most of the times you end up at, even after 10 epochs for a long time, you end up at the point basically it's 10% accuracy. And you have 10 classes. It means that you are random. You are basically, it's not an interesting point. That's not just the step size. If you repeat it, for example, for different batch sizes, you see the same thing. Regular minimization, it almost always converges in our experiment. Min-max many times doesn't converge. It's also like if you find the best batch size, best step size that works for everyone, but just randomly change the seed value, the regular minimization always converges, but the min-max formulation doesn't converge in many cases. So it's basically not a very reliable algorithm, and we have seen like what the issues are. So this min-max, it's not that they are hard in extreme cases, as Manolis was talking about it, but also the hardness we see it in practice.
Sorry,
Sure.
Two questions. So the fact that, first of all, the accuracy isn't great doesn't mean it didn't converge. I mean, we have to separate the two.
That's a very good point. Okay,
Yeah.
that's a very good. But we checked. Okay, we tried to see whether it's convergent or not, and it's not. But we could not like plot that and show it very well. Like it's jumping around. So we could like if we could like plot it in a 2D dimension, we could start to see it, but we have a lot of like variables. That's a very good point. So and then we know that certain stationary notions are difficult to compute, as we saw talking this morning. But min-max problems, they appear in practice. So now I ask a question of any solvable problem instances or any solvable problem classes that we can focus on for min-max. And when I talk about solvable, we have to decide what do we mean by solvable and what is the solution concept that we are looking after. Generally, at the high level, we can think of min-max formulations as a bi-level viewpoint or Stackelberg that your goal is to minimize this G of theta, okay, which is the max, is defined as max over alpha, f of theta and alpha. So your final ultimate goal is to work with G. So G matters for you. Another way is to look at it as a game, Nash game. You have two players, alpha and theta. And you can define your notion of optimality or stationarity based on the viewpoint that you have. For example, on the Nash viewpoint, you are happy if, for example, in the unconstrained case, your gradient narrow norm with respect to theta and alpha is small. The constraint, you can look at the proximal gradient norm, for example. In the bilevel stack or Stackelberg viewpoint, which I focus on just during this talk, our focus is we say that theta star is a reasonable station point if the gradient of G is small. G is a small. Again, G may not be differentiable in general, so we are going to use Morrow envelope of G, some smooth version of that. It says we use Morrow envelope in this talk. So, and the two solution concepts are in general different. They don't coincide. You can come up with simple examples, such as this example. You can also add like bounds if you want, theta between -1 and 1. In this example, if you plot the G function, which is this maximum, this is your G function. It's nice convex function. And the only reasonable solution seems to be a theta star equals to -1 if you look at it from bi-level viewpoint. But if you look at it from game perspective, the Nash equilibrium or first order Nash equilibrium or the solution to VI is 0 and 0. So they don't necessarily, the solution concepts coincide. But in some cases, such as non-convex concave, when your F is concave in alpha, you have a compact set A, then the two solution concepts coincide. And during this talk, as I mentioned, I'm looking at this bi-level viewpoint. And the reason is that one of the motivating examples, the motivation is robustness. And when we look at the robustness, we want to find a parameter theta that works uniformly well or well across all choices of alpha. So what matters for us is mostly this G. So now that we know what solution concept we are looking for, let me talk about what algorithms we are looking for. So the algorithms, again, I listed the properties that we have nice properties when we focus on regular minimization. For example, when we looked at gradient descent, we saw that the objective function improves over iterates. It means that when you start, you stop after like an hour, you are almost certain that you get a better point. If the algorithm stops when you are using projected gradient descent for minimizing a function, the algorithm stops or jump around, or you go to like, you look at the limit points, they are stationary. And for nice problems or convex problems, these are optimal points. And the convergence rates are dimension independent. Now, I want to focus on algorithms that they have also these properties for Minimax problem. And this is a summary of basically the results that I'm going to talk about. So 3 cases we are going to talk about and the rates that we get. Basically, the 3 cases that we can have an algorithm that satisfies those properties is when your F is concave in alpha, when you have a small adversarial domain, is that the diameter of this constraint set A is small. It's comparable to your desired accuracy. And then you have a small coupling, meaning that the smoothness parameter that corresponds to this Hessian with respect to theta and alpha. You take the first derivative with respect to theta and measure like the second order derivative with respect to alpha, this thing is small.
That's the quick verification. Those 3 are independent. I mean,
no, these 3 are like not, yeah, these are or, not and. Okay. So if this happens or this, you can come up with an algorithm. That's a very good point. And we again find a station point for G. And the algorithms are going to almost always improve the objective at each iteration. improve your G. So let me start by the simple case of non-convex strongly concave setting. So again, my aim is to minimize G. So let's try to minimize G. I can try to apply gradient descent on G, but we don't have access to the gradient of G directly. So this is projected gradient descent. This plus means that I do projection. But I don't have access to the gradient of G, and it's well, it is differentiable when the function is strongly concave. But I indirectly have access to the gradient of G through Donski's theorem. Donski's theorem says that the gradient of G at the given point theta naught is the same as gradient of F at theta naught when you replace alpha with the optimal alpha. So if you find the optimal alpha and take the gradient of F, then that gives you gradient. And this simple observation gives you basically an algorithm. So you can have an algorithm like this. You approximately solve with respect to alpha, solve this maximization, and then you do one gradient descent step with respect to theta. And you can show it like a convergence result. This is what we show like very early with Jason and Mazi are here also in the audience. That if you run this algorithm, you need order epsilon minus 2 up to logarithmic factors of gradient evaluations for computing epsilon stationary solutions. And the reason for this rate is that you are mimicking the behavior of gradient descent on the function G, which is this max. So this is the number of gradient descents that you need. This needs from the classical result of non-convex smooth minimization. You need to order epsilon minus 2 iterations on theta. And this is strongly concave, so you need logarithmic. You have logarithmic dependence on epsilon. And it's up to logarithmic factor optimal. You can generalize this also to PL cases. So you need to establish Donski's type result for PL under PL assumptions, but you can do that. So that tells you that if your F is also not strongly concave in alpha, but strongly concave composite with affine, you still can get risk rate. Now the next step is that can I relax it a little bit? So let's relax this strong concavity assumption and go to concave assumption, concave case. So what happens when you have non-convex concave scenario? So now our F is concave in alpha, but not strongly concave. Again, I can try to apply gradient descent or some descent method on G, but G is no longer differentiable in this case necessarily. A maximum of concave function is not necessarily differentiable. So a simple trick is to smoothify G. Okay? So I can smoothify G, basically use the idea, the algorithm that we had before. I make it strongly concave first, with respect to alpha, and then I apply our previous algorithm. I just need to make sure that my lambda is small enough so that it gets me the desired accuracy. And again, the algorithm would be you do gradient descent on theta. So we try to mimic the behavior of this gradient descent dynamics on G. And using Donski's, again, this is a high-level description of the algorithm. You apply some algorithm, some first-order algorithm, gradient ascent, for example, to solve this problem. And then you do one step of gradient descent with respect to theta. And you can analyze it. If you, for example, do Nesterov to get a faster rate. This tells you that you need this, you can analyze, and you see that you need order epsilon minus 3.5 gradient evaluations for computing stationarity in terms of the Nash equilibrium viewpoint, and epsilon minus 4 in terms of Stackelberg viewpoint. As I said, when you have concavity, the two notions are related, so you can compute the number of gradient evaluations for both of them. So any questions so far? Okay. So the question that I want to focus is that why does it become so much slower compared to the previous case? We had a strong concave case, which was epsilon minus 2. And now we went to epsilon minus 4, or epsilon minus 3.5. Why we lose so much rate? Or why do we observe significant rate drop? The reason that we observe significant rate drop is that if you want to find epsilon stationary point, as I mentioned, this problem should be a good approximation of this problem. To guarantee that the point that you get, the solution that you get by solving this problem, is indeed the solution of the original problem, you have to choose your lambda small. It turns out if you analyze it, your lambda should be ordered the epsilon. In fact, to be accurate, it should be epsilon divided by the radius of the constraint on alpha. And so when you choose lambda to be ordered epsilon, and you minimize this g of lambda, which is this max, what we know is that the step size that we choose should be inversely proportional to the Lipschitz constant. So we know, like we also learned from the last, during all of the talks, the step size that you have is 1 over L, the order. So it turns out that the Lipschitz constants of this g lambda, you can analyze it, it's not very difficult, is indeed inversely proportional to lambda. So your eta depends, it's inversely it's 1 over Lipschitz constant of g, and the Lipschitz constant of g is 1 over lambda. So in other words, your eta should be ordered as epsilon. So your step size should be very small if you run this out. And we know it's like, we know that you cannot use arbitrary step size. You cannot, because if you choose it very large, you may go and increase your objective function. But if you can look at the future, so if you can look here, when I'm moving here, I look here and I see, okay, my gradient is going down very quickly. It seems that my Hessian is large, so I can take larger step size. And that is the idea of proximal point algorithm that has been seen also multiple times during this workshop. In particular, if we can follow this dynamics, you can choose arbitrary step size. Okay? So if I choose any eta, this algorithm guaranteed gives you decrease. And the reason is that this dynamic here is equivalent to this one, the proximal point, which you can see that when you do g of theta t plus 1 is less than or equal to g of theta t, no matter what eta you choose. So if we want to choose a large step size to have a faster convergence rate, you have to follow proximal point. It seems one idea is to follow proximal point trace. So if I want to apply proximal point on this minimum for minimizing g of lambda, each step I need to solve this optimization problem or this subproblem. But this might not be easy. So let's first replace the definition of g of lambda here. G of lambda is the max of this function. So I need to solve this problem. Again, if I try to solve it in this order, okay, I want to basically replicate this dynamic using a gradient dynamics, okay? Because we want to work with the first order method. So we want to use the gradients of f. Now the question is, how can I use the gradient of f to follow this dynamics to replicate or mimic the behavior of this type? So again, if I do it in this order, then again, I have a strongly concave function inside with respect to alpha with a small lambda. And that gives me a large Lipschitz constant for the function, which is the max of this. Okay. So, and that gives me basically, again, a rate drop. So what you can do, but right now, is that since this problem right now is strongly convex, strongly concave, because after you add a regularizer, this becomes strongly convex in theta and it's strongly concave in alpha, you can switch min and max. Okay, and you can solve it in this order. So what happens here is that right now, if you, for example, you choose your eta to be 1 over Lipschitz constant, you have an optimization problem with the constant condition number in theta, because it's you can make the strong convexity modulus of theta to be order L, you can make it L half. And then, so the inner minimization now can be solved order constant, okay? Because it's strongly convex, or up to logarithms. this the solving the minimization strongly convex is order square root kappa log 1 over epsilon, right? So kappa right now is order 1, so you can solve this minimization. Inside minimization order constant. And for the outside, when you solve it, you can get to any desired accuracy that you want. You can get the gradient of the outside problem. And for that, you can use, for example, now Nesterov acceleration for the outside. And you can repeat this. Basically, you can repeat this algorithm, and that gives you this rate of convergence. It's actually very easy to establish this just by using the building block, existing building blocks of Nesterov acceleration, combining basically to solve this inner minimization with the gradient descent with respect to theta. Then you do accelerated Nesterov outside, and when you have the desired accuracy, you update your theta, go to next. Yes.
To be clear, the switch of min and max only holds for eta that is very small, correct?
Yeah. So it's
because the function f is not convex in theta.
So I choose my eta to be 1 over 2L, the Lipschitz constant of f. Okay, and if I do that, this becomes 1 over 2 eta becomes L. Okay. So if you add L, now your Lipschitz constant of your entire function with respect to theta is 2L. Your strong convexity modulus is L. We have 2L over L. Your condition number is 1. But yeah, that's correct. So
With respect to it was connected with the Hessian of it.
yeah, so Lipschitz constant of the gradient, which is connected to the Hessian. Yes. Yeah, that's. So you get. Did I answer your question? Okay. Good. So you get this rate of convergence, and similar rate of self-convergence actually has been observed also like in other works. Particular, for example, Kong and Monteiro has a similar they get a similar rate of convergence, but they assume, for example, one difference is that they assume they have access to the gradient of the smooth version of the function, which is different than having access to the gradient of the original function, because it's not clear in different applications how do you get access to the gradient. This paper, which appears like a few weeks after us, it resolved this issue here. But particularly these two references and both are, they also have similar results, which I want to spend one slide talking about the differences in terms of the result, because this was actually one related to one technical aspect that helped us use all the building blocks in the literature. So these two works also get the same rate of convergence, although it's for constraint and Euclidean proximal. The result that we have, it was for, sorry, these are for unconstrained. You can work for constraint. But the most important thing for us was that when we tried to work with the standard or the stationary notion that's been used on the other works, we had like technical difficulty connecting the accuracy that you need to solve the inner problem to the outer problem. So, and then the main difference, actually, one of the main difference is that in terms, it's in the definition of stationary notion. To explain what is the stationary notion difference between this work and the existing works, which helped us also to establish convergence very easily without using the building blocks without developing our own acceleration method. So we use, for example, existing Nesterov acceleration instead of developing our own. Is that to explain this stationary notion, let me consider and explain it for simple minimization problem. When you minimize a function h constraint, okay, I'm going to define two stationary notions. The first one is the gap in the proximal, which has been used a lot. This is the second one. They both may seem ugly right now, but they have both been used in the literature before. But I'm going to tell you that these two stationary, I'm going to explain what they mean, okay, in a second. But before that, I want to state the theorem that this stationary notion is a stronger notion in the sense that this stationary notion implies the first one, but the first one does not imply the second one, like for any epsilon prime. Means that you may get this one for epsilon, but you do not have this for any epsilon. Okay. And why do we have this? So let's understand these stationary notion definitions. These are, you can define it for general, proximal, but let's understand it for projection based. So a point Z star is optimal or like stationary for this problem. When you go to the negative direction of gradient and project it back, if you come back to Z star, then we say that this Z star is a stationary point. Okay. That's been used a lot. Also, we can think of it as a solution of VI. Okay, this is the explanation of the solution to VI that you have. Now, if you have another point, Z bar, that's not optimal, meaning that when you go to the negative direction of gradient and you project back, you come to a different point. I'm going to form this triangle. And I'm going to use alpha, beta, gamma to denote the length of different sides of this triangle. So the first stationary notion says that after you project this point minus this point, this should be less than or equal to epsilon. I ignore the normalization with the Lipschitz constant. So basically, I assume the Lipschitz constant is 1 for simplicity. This stationary notion says that we are epsilon stationary if your gamma, the length of gamma is less than or equal to epsilon. The second one tells you that you can simplify it and work out like the geometry. The second one tells you that if alpha square minus beta square is less than or equal to epsilon squared. This is the second stationary notion. And the proof of this theorem is very simple. Actually, you can use the law of cosine because we know that this angle between beta and gamma is obtuse, is more than 90 degrees. So we know alpha square minus beta square is larger than or equal to gamma square. Okay, so that tells us 2 implies 1. And it's not very difficult. It's very hard to see examples that these are along the same line. And this gap could be very large. Questions? Any questions so far? Okay. So what I'm going to do, so this was basically our result, but for non-convex concave setting. Now we ask a question of, now the next question that I want to ask is like, how much can we go beyond the non-convex concave setting? And again, I'm looking at the bilevel viewpoint. And I'm using 2 motivating examples, 2 simple examples. If I have decoupled cases, a problem like this, okay, although it's min-max, it might be non-convex, non-concave. But if you're interested in solution in terms of theta, it's easy to solve it, right? Because you just apply gradient descent on F1. Because F2 is like irrelevant, it decomposes. Or if you have a problem, min-max problem like this, that your constraint is a singleton. If you have a singleton, this, again, min-max problem is artificial and min-max. It's essentially a minimization, both of them, right? Because this max is not relevant. So these are 2 very corner cases that min-max problem is easy. Now, if you relax it a little bit, essentially the result is that if your coupling is small between theta and alpha, or the diameter of A is small, then you can solve that problem of the stationary notion. And the idea is that we may not be able to evaluate G exactly to take its gradient, but we may be able to compute and evaluate the approximation of the gradient. Sorry, the gradient of our approximation of G. To give you basically technical result, if this is the original problem, we essentially use a Taylor expansion. Let's look at the Taylor expansion of the problem. Okay. So instead of G, I will use the Taylor expansion of it, where I take the max over F tilde K. F tilde K is the kth order Taylor expansion of F. The Taylor expansion is with respect to alpha only, so it's not with respect to theta. And we know that this could be a good approximation. This is a good approximation. If, for example, the radius of A is small, if the diameter of A is small, the Taylor expansion could be a reasonable approximation. So now there are two questions. If I solve this problem, is this related to the solution that you get? Is it related to the original problem, the solution? It's the first question. The second question is that can we solve this problem? Okay. So I'm going to answer the first question first. Is that solving the approximate problem solve the original problem to the desired accuracy? And this is that simplified theorem that assume that the diameter of the constant set is A. If this condition is satisfied, in other words, if your diameter is like order of your desired accuracy, or like your coupling is small, then any epsilon stationary of this point is an epsilon stationary of the original problem.
What's in the square root?
Oh, very good. Yeah, sorry. So first of all, K is the order of approximation, Taylor expansion approximation. L theta theta is the Lipschitz constant of the gradient. So when you take the derivative of f with respect to theta, I measure the Lipschitz constant with respect to theta. In other words, you can think of it if your function is in C infinity or in C2. You take second order derivative with respect to theta, first and second with respect to theta, and this is the bound that you have for this. L theta alpha is a bound that you take the first order derivative with respect to theta, a second order derivative with respect to alpha. And there is L alpha k plus 1, which is the Lipschitz constant on, or the bound, when you take k plus 1 order of derivative with respect to alpha. Is that? And d alpha is the diameter of this set, constraint set. So this essentially says that, for example, if I look at this term, if this is less than or equal to epsilon, what does that mean? It means that if your d alpha is small, if your radius is small, or L theta alpha is small, means that your coupling is small relative to your desired accuracy. These are the two corner cases that. Then you can get the epsilon stationary solution by solving the approximate problem instead of the original problem. Questions? Did I answer? Questions? Okay. Yes.
L alpha k plus 1.
Oh, L alpha k plus 1 is the Lipschitz constant with respect to alpha, the kth order. Okay, so you take k plus 1 derivative with respect to alpha, and that's the upper bound in the form of that. Yeah. So this is true for any k from 0, 1 to whatever k you want. So for example, as alpha is 1, this would be the Lipschitz constant k, it would be alpha 2, or you can think of it alpha alpha, which is you take 2 derivative with respect to alpha, and that's the upper bound that you have.
So I want to understand, that means that if my function is enough smooth, and I am in a bounded space, for example, so, and the diameter is polynomial, for example, that means that I can solve the Stackelberg equilibrium efficiently?
No, this is up to epsilon order, but epsilon is above this. Okay, so you can go to this epsilon. You cannot choose epsilon arbitrarily.
I cannot go lower than this.
You cannot go lower, at least by this approach. Okay. And this tells you that when, for example, but this epsilon, this value could be small if your d alpha is small, or like L theta alpha is small. So this is one way of looking at it, that in some coordinate cases you can solve it, or you can think of it as you can solve the problem up to this accuracy, not beyond. With this approach, at least.
Say super large, I should be able to get smaller. Is that?
Can you say it again?
Say it's super large.
Uh-huh.
I use very high order Taylor. I should epsilon should be very small.
So there are, okay, so you may be able to get smaller like epsilon, but larger k, but solving the approximate problem, that's not easy. Yeah. And you go for a larger k. So any questions? Okay. Yes.
One last question. So the result is the constructive or mathematical, with the meaning that
So this result is saying that if you find an epsilon stationary of this
independent of the
problem,
algorithm.
independent of the algorithm. is an epsilon stationary of this term. At least with this approach is the results are order type, meaning that the epsilon station, if so, you can think of this as additive term that basically the epsilon accuracy that you solve this problem and the epsilon accuracy that you have this. This is the gap that you have between the two. You can think of this as this. And this is, you can say, show this order type, meaning that there are problem instances that you can construct the problem instance that you cannot go beyond this with this strategy. Is it clear? Okay. So the next question is that can we solve this approximate problem? And this is that it's actually easy. So let's specialize it, for example, for k equals 1. So k equals 1, if my Lipschitz constant, for simplicity, assume that they are 1. So my d alpha should be order epsilon. Okay. And that tells us when your radius of A is order your desired accuracy, then instead of solving the original problem, you can solve this problem. Okay. And this problem is non-convex concave, meaning that it's non-convex in theta, but concave in alpha. Okay. So you can use the algorithms like that we talked about. You can get overall iteration complexity of O epsilon minus 2, but you need to have access to the gradients of this function, which would be the Hessian of the original function, because you need to take the derivative of this term. This gives you the Hessian. You can relax that by using the finite differences. If you specialize it to k equals 2, that tells you that our bound tells you that if your radius is order epsilon power 2/3, okay, instead of solving the original problem, you can solve this problem, and you can relate the epsilon stationary. And this problem, for example, when the set A is Euclidean ball, this becomes a truss region subproblem. And this is a truss region subproblem, and you can solve it. You can solve the inner maximization problem using first order methods for truss region. There are many of them. You can, for example, use this or Carmenducci, and we show that overall algorithm that you can get, you can using this method, you can have an algorithm with this order iteration complex for this class. Questions? Okay, so these are two special cases. My time is over, so let me conclude and I'll take talk about some open questions. So we talked about 3 special cases that min-max problem. In the bi-level viewpoint, stackable viewpoint, they're solvable, but there are many open problems still. The lower bound on non-convex concave sibling is open. The requirement set, for example, I had for k equals 1 and k equals 2, which is your d, your radius be this order or this order. This is tight using our approach, in that using the Taylor expansion approach, you cannot go beyond this. But can I relax this diameter further? Is there any other algorithm that, for example, can improve the radius requirement? Epsilon, for example, minus 1/2. Epsilon 1/2 instead of epsilon 2/3. The iteration complexity bounds that I talked about for quadratic case is not also, we don't know whether they're optimal or not. This is also open question. These are some of the references with many of the colleagues on the min-max problem. I want to thank all the colleagues and some of the supporting my research. And if you have any questions,
any questions?
So on your algorithm for non-convex concave, you have this like strongly convex, strongly concave problem.
It was non-convex, strongly concave.
But when you
I can specialize it to strongly convex, strongly concave.
I guess,
oh, you mean the sub problem?
The sub problem. Yes,
Oh, okay,
yes.
okay, good.
So
This one.
yes, exactly. So I guess I don't remember exactly the results, but I think there's been some work on solving these problems when like the condition numbers of the maximization, minimization parameters are unbalanced. Is your like algorithm that solves this problem, like get the optimal dependence on the condition
That's a
numbers? or
very
is there
good
better
point.
way?
Yeah, you can actually, I think there is a result by Tianli and like there is also that they talk about optimal rates. This algorithm is actually simple switch also gets that right.
Okay.
You can show that gets that. That's right.
Thanks.
So you can like this simple, like using proximal and following this proximal, mimicking that gets the same. Which is order optimal. People have already established some lower. Question. All right.
Thank you again.
Thank you.
And we're back at 2 p.m.